Okay, so again, we're on chapter 14. We've talked about acids. We talked about weak acids and how they appear in a chemical equation, right? You remember how we treated weak acids when we got to the net ionic? Remember that? To where if we have a weak acid, what's our strong acid, by the way? Can you tell me? Remember?
HCl.
Okay, HCl is one.
Nitrate.
Nitric acid.
Bromic.
Hydrobromic.
Is it HF?
Not HF.
No.
HI.
HC. Oh, wait, another one.
HCl.
We already have it.
Oh,
We already have it.
three.
O.
Three.
4, isn't
I
it?
think it's O4. And there's one more, H2SO4. The first hydrogen that comes off would be considered the strong acid. The second hydrogen that would come off, you can kind of see some cases where these strong acids don't have a Ka value. So if you remember, when we took our quiz, you guys had to set up to solve for different concentrations based upon the constant. The constant was really small. It did not affect our initial concentration. So weak acids, we're going to work the same way as what we did last chapter, dealing with that K value and solving for X. Because the weak acids, they do not dissociate very much at all. 1 or 2% at the most. Okay, so strong acids, they break apart 100%. 100%. So if we would show those breaking apart, they go HCl, arrow, H plus Cl minus. If we would do that with all of them, that's what they would look like. Okay? They break apart 100%. And so some of you are like, well, what would it look like if they didn't break apart 100%? We can kind of show you what those would look like. Okay? So weak acids, we'll just go ahead. Everything else is a weak acid. So if it doesn't encompass those 6 acids, then they're considered weak acids because they don't break apart 100%. Okay? So this would be aqueous. This would be aqueous. Aqueous. Okay? When that breaks apart. Okay? So we got this thing called weak acids. What are weak acids? They break apart very slightly. Maybe 1 or 2% at the most. So dissociate, small percent means they just dissolve, break apart. Very, very small percentage actually breaks apart. So if we remember when we wrote those out, for example, we have a weak acid like H, HF, it's a weak acid. Then they break apart. We have a double arrow. So that means after so much of the ions form, guess what they'll tend to do?
Go back.
They'll go back. Okay? On this one, it's a single arrow. They don't go back. HCl breaks apart. They don't go back. They don't get together to form HCl because they break apart 100%. Once they do, once they are saturated, they won't go back together. Okay? Here, there's a double arrow means that we're going to have an equilibrium constant on these. So weak acids will have what we call an equilibrium constant, or called a Ka. We would set it up the same way. So what we would do, if we set this up to solve for the Ka, we'd do it the same way as what we did last chapter. So what would this look like when we would set this up to solve for the Ka? So the Ka would equal what? Divided by what?
Concentration of hydrogen.
Yep, the H plus concentration
Fluoride concentration.
times the fluorine concentration, which is going to be the same, divided by the initial concentration. Well, not the initial, it would be the final concentration of it. So if I wanted to solve for the Ka, that's what we would do. So now there's a list of a bunch of Kas you need to be familiar with. They won't come up until later on in the section, but if you turn over to page 658, they give the Ka values to you at 25 degrees Celsius. Okay, so in your book, if you turn over to page 658, they give all those Ka values. And so if you go down through it, you can kind of see some of the different type of acids that we're going to be dealing with and what their constants are. If you go to the very bottom and you look at phenol, that H coming off of that group, that is a very weak acid. The smaller the Ka value, the less it dissociates. So small Kas means that you don't make very many hydrogen ions. And the hydrogen ions are what make something acidic. So if I have a small Ka, that means my concentration of hydrogen ions would be small. My products are small. If you go up above there, you can find HF. And HF, hydrofluoric acid, has a Ka value of 7.2 to the minus 4. So that'd be small. And if I had to solve for hydrogen ion concentration, I could do that. Okay? I could do that. So we're going to do one of these real quick. These are really easy to do, especially last chapter. You guys know how to do ice. So I'm going to give you initial concentration of HF. And we're going to go through a sequence of solving for H plus and fluorine ions. And then once we've solved for the hydrogen ions, we're going to introduce this concept called a pH. pH scale, we're going to go ahead and share with you here in a second. But a pH scale is a way to tell how strong of an acid you do have. Okay? And that's where our indicators kind of come in. We use phenolphthalein, it's pink, as pH of 7. If you go above a pH of 7, it turns kind of to a darkish red color. If you go down below 7, it's clear. That's where you get that clear to pink, and then it goes all of a sudden. Bromothymol blue you guys used in your lab. I believe it went yellow as an acid, green is neutral, and then it was blue as a base. Okay, so that's a different type of indicator as well. For the most part, they work out that way. Okay? So let's go ahead and do that. Let me go ahead and give you initial concentration of HF, and let's make it 0.25 molarity. That's our initial. Okay? So then, when we look at that, it's just HF concentration. Break it down to H plus F minus. Okay? So we still use our ICE. this is our initial, 0.25 molar. And then we have 0 and 0. Now we want to see how it kind of dissociates and breaks apart. So we do our change. We go ahead and set it up. We solve for X. Our X is going to be our H plus and our fluorine concentration. These are really nice because every time you break these apart, they're just going to give you X values. You're not going to have a plus 2X or plus 3X because we're just breaking apart one hydrogen off, and then it leaves behind a anion off. Now, this is called this can be called a hydronium ion too. And today, I don't think I'm going to go through what's called conjugate acids, conjugate bases, those type of things. We'll do that on Tuesday when you get back. So go through and do that calculation real quick. Should take you about a minute and a half or a minute because it's really simple setup. But anyway,
You get final one, two, four.
so just real quick, you get minus X plus X plus X. Then you have 0.25 minus X, X, X. Then we have basically X squared over 0.25 molar minus X. That equals your constant. Your constant is small enough that it's not going to change. It might change our initial concentration a little bit, or final concentration a little bit, and we can look at that later, but we're not going to look at it now. But that's 7.2 to the minus 4th. So then all you really have to do is you get rid of your X. So then it becomes what? Square root, right? 7.2 times 10 to the minus 4th will give you your X. And you said that was what? 0.0134.
134. You have to multiply the 0.25 to the 7.2, don't you?
What's that?
You have to multiply the 0.25 to the
Right, right. Okay? So that's our concentration of our H plus and our F minus. So if they ever ask you to give the concentration, then you can just go H plus and F minus equals 0.034 molarity. Okay? Now we're going to have to convert these over into pH. And I don't remember when you guys went through if we did a whole lot with pH. And if we did, you probably don't remember a lot about it. If you guys would get out your calculations based upon what's going to be given to you on the AP test, we'll take a look at some different sections on there that give you information about how to solve for pH and how to do that. So, if you look under, I think they're equilibriums, and they should be giving you some values for finding pH. Do you guys see some examples? Okay, so what do they say about your calculating of a pH? What are some different ways you can do that? pH equals what? pH equals the minus log of the H plus concentration, right? Okay, do that with our last one. Go ahead and find the pH of our solution that is 0.25 molarity. Okay? So it was 0.0134. That tells you how strong the acids are. Okay? So go ahead and do that if you would. So you log it, you come up with a negative number. You have to change the sign of that with the negative out in front. So what is the pH of that solution? 1.87 or 1.9. Okay? So if I had a pH meter and I put HF 0.25 malaria, I made it up, and I would test it with a pH probe, it would come up to be around 1.9 is what it would read, because it'd be reading hydrogen ion concentrations. Any questions with that you have? Okay? Well, let's take the strong acid. So strong acid doesn't have a Ka. Okay? So strong acid does not have a Ka. So let's just take HNO3 for example. Let's say I have 0.025 molar of HNO3. So then I have HNO3, one arrow, not coming back, forms H plus NO3 minus. Okay, so we're starting out with 0.025 of this. And when it breaks apart, we're not going to use ice because there's no equilibrium here. When it breaks apart, it's going to break apart 100%. What's the concentration of hydrogen ions?
0.0125?
No, 0.025. Because for every HNO3 that breaks apart, you form one hydrogen, one nitrate ion. So they're both 0.025 molarity. Go ahead and find the pH of HNO3 now. 1.6. So how do you do it? pH equals minus the log of the H plus concentration. So we're going to go ahead and take minus the log of 0.025. So initially, I want you to look at this. Initially, we did, and I'm not going to go back to the screen, it has a concentration. What was the initial concentration of HF?
0.25.
2.25. So this is a concentration of HNO3 that would be 1/10 of HF concentration, right? Of just the overall concentration of the original solution. So this is 1/10. But this is almost as strong of an acid, even though the concentration is 1/10, because it dissociates 100%. Okay? So what did we come up with that? 1.6?
Yeah.
Okay?
So, irrelevant question here, but does pH stand for like positive hydrogen?
It's the power to the 10th. So everything, if we compared an acid that's a pH of 5 compared to pH of 6, the one that's pH of 5 has 10 times more hydrogen ions in it than a pH of 6. So it's based upon the power of 10.
Well, like, I was just wondering what pH stood for, because they never...
The reason why they developed pH is so that workers in industry would not have to work with numbers that have to deal with scientific notation. So what they've done is they've developed a way, we're just going to take that very small concentration, because they can be really small concentrations, even smaller than what we're doing. And then when you log those numbers, you get numbers between 0 and 14. So the pH scale is set up like this. It's usually going to fall in the range between 0 and 14, 7 being neutral. So 7 is neutral. This is the strongest acid. So this is strong acids down here, considered. So those two that we did, they're around 1 something, but they're stronger concentrations, I would say. Not strong acids, but they're stronger acid concentrations down here. Because you're saying, well, HF was 1.8, so wouldn't that be considered a strong acid? What depicts a strong acid is if it breaks apart 100%. And up here, we have stronger bases. We haven't talked about bases yet, but we're going to go ahead and do that here real quick. And in the middle, you have neither an acid or base, it's neutral. So on this side, these are all acids. You could have a negative number too. It can go beyond the 0. We can have a negative 10. Okay? Or not negative 10, but a negative 1 we could have. If you have a negative 1, the pH would be, I believe the pH would be like, or concentration would be 1 molar. Okay, and I think like negative 2 would be like 10 molar concentration, which, I mean, those are extreme concentrations there. Okay, compared to what we're going to be dealing with. Up here we have bases. It's all about the base, right? No, it's not in chemistry all about the base. Acids get more of a do than the bases do. Okay? Alright, so we have this thing called a base that we want to deal with next. And these bases, the traditional definition called the Arrhenius definition of an acid is anything that produces hydrogen ions. So anything that makes H+ ions is considered an acid. Anything that makes OH ions, which are hydroxide ions, are considered bases. So anything that makes OH ions is considered a base. So when we think of bases, they're pretty much going to be strong bases and weak bases. Okay? So the strong bases are metal hydroxides. So anything that's a metal hydroxide that dissolves, that's soluble, and considered a strong base. Okay? And then weak bases, we're going to wait. I'm not going to talk about weak bases now. We're just going to deal with strong bases. That kind of weak bases will come a little bit later, and we talk about those. They're not as easy to identify. Ammonia would be an example of one that would be a weak base. So if you had to come up with a weak base, ammonia NH3 is a weak base. So if I have say a 0.25 molar solution of NaOH, it dissociates 100%. So strong bases, they break apart 100%. So we got NaOH, and then it breaks apart into Na plus OH minus. 100%. So if this is 0.25 molar, then this would be 0.25 molar, and this would be 0.25 molar. Okay? So, again, those strong bases dissociate, break apart 100%. Now I'm going to have you find the POH. Now if you look on your chart, there is a POH. Does it look familiar to pH? Yeah. Instead of using hydrogen ion concentration, it's using what? OH concentration. So what we would do is we'd take the negative log of the OH ions, and that would give us our POH. Now we don't use POH a whole lot. We'll have to convert a lot of these POHs to pHs to see how they would fit on the pH scale. And that's what we're going to do with this one. So we go ahead, we do the same thing, minus the log of 0.25 molarity. And we get an answer out that is what? 0.6. 0.6 is a POH. Okay, any questions with that? Pretty easy. Okay? Now, here's this real simple way to convert pH to POH. They have this thing called a kW. You see the kW there on your sheet? KW is a constant for water. So any solution that you have will come out to be a constant at 25 degrees Celsius. That would be 1 times 10 to the minus 14.
It says 13.
Does it?
Says 14.
I think mine says
Oh,
14.
it's 60 degrees Celsius.
Right, we're doing it at 25. Room temperature. Okay? So that's what the KW equals. Okay? So if we would log that number, so guys log that number. What would you get?
Negative 14.
But, and then take the negative of that like we do pH and POH, you get 14, right? So if you look down below, there's this equation. It says 14 equals the pH plus the POH. And it comes off of that idea of KW. So if we log KW, and these are negative logs as well, that's what we're going to do. So let's say we want to find the pH of that solution that we broke apart. Okay, is that NaOH we broke apart? So then 14 equals the pH plus 0.6, right? So then what's the pH equal to?
14 minus
Yeah, 14 minus 0.6, which would be 13.4 on our pH scale. Okay? So when we look at our pH scale that we have, there it is, up here, 13.4. So it's basic. It's a strong base. That base you wouldn't want to kind of mess, especially if it's pretty concentrated. You don't want to mess with those. Bases are bitter, they're slippery, and they're pretty damaging when you get them on you. We did a lab where a student, remember the penny lab that we did where you had to coat the penny in zinc? We had to use a strong base, about 8 molar NaOH. You could probably log 8. And when you get the POH for that, it's probably going to be a negative number, which would make it up here above 14. And he had a little bit on his fingers, didn't know it. He rubbed his lips. Next day he came in, they were blistered. Yeah, they were blistered. So, I mean, it just reacts with the skin just like HCl would react with the skin. Okay, you start itching. When you get base on you, especially when I've done stuff in the past, get a little base on you, I start itching. And usually if I know I'm itching, it's because I got some of it on me. Okay? So it starts reacting with your skin. But his, I don't know why, he didn't notice it, or they just stayed on there and they blistered his lips pretty good. Right. I went through a lot of information here. Okay? They give you a wealth of how to solve for Ka, Kb, Kw is just using the initial concentrate or the final concentrations of those. Just a wealth of information of how to go through and solve for some different quantities. What I'm going to do is give you an assignment over break. And the reason I'm doing this is we're just running out of time. There's some things that we've done with labs that take a little longer. We have some things coming up where we've got an hour and a half we're meeting, so instead of 2 days going through some things, we do it in 1 day. And so I'm going to give you a short assignment dealing with pH, POH, dealing with Ka values, solving for those. So let me give you that. I'm going to probably change it up from what I had before because I switched it around. This chapter will go pretty quick. We won't do much labs with this chapter. I think more so maybe the next chapter with titration with weak acids that are a little bit different than strong acids. Okay? Let's just do one where you have a pH. So let's say our pH is 3.5. Okay? So what we're going to do to find out the concentration of that, we're going to go ahead and put that into the inverse log or the anti-log button. We're going to go 10, and then we're going to go, when we push that button, we're going to push that button, and it's going to be minus 3.5. So why don't you go ahead and do that on your calculator, that function.
I thought it was E.
Nope, not on this one.
That's natural.
Not natural log.
Right.
Nope.
Sorry.
Come on, Caitlin. Doggone it.
It's negative?
You'll have to put the negative in front of the 3.5 if you want it to come out the right concentration.
3.2 times
I
10 to the
got
negative
it.
fourth.
Yep. So 10, hit that button, in parentheses, put a negative. You got to use a little negative. Can't use the negative that you use subtraction for. So what'd you get for that? It'd be what?
3.2 times 10 to the negative 4.
Okay, and that's H plus concentration. Okay? So that's how you would do a problem like that if you have to go backwards.
What page is this on?
This is page 704.
Okay, that's fair.
So 59.
Stop.
704, you said?
65. Do 67, but the last part where it says to find the percent dissociation, don't do that. This says determine the concentration of all your stuff in there and the pH. That's all I want you to do. Don't do percent dissociation. We haven't done that yet. And then number 89. And these are all odds that you can check your answers out as you go. That'll be it. Okay? 55, 59, 65, 67, and 89.
Will you guys stop doing that?
Take the ink out of my pen.
So you put my book away. Then I'll stop doing this.
I take the ink out of my pen. You're running
Stop
my empty
it!
pen.
Stop!
I can't make you mad. You choose to be mad.
You
want
choose
that.
to do things that irritate me.
Guys, somebody's going to watch
You
this
want
video.
Tyler
That's
shoes.
not-
That sounds like that. That sounds like that guy we used to watch a movie and I had Becca get it on Netflix.